Today, we're going to talk about scaling visualization for big data in the cloud. So we're going to approach this problem on two fronts, beginning on the engineering side of things. Like we're going to talk about different scaling strategies that we apply on our cloud infrastructure on the cloud resources. And then we're going to talk about principles and strategies that we apply for converting data into visualizations and the usage of different proven visualization blueprints that we apply on market surveillance data set. So before we begin, I just want to spend a couple of minutes on what FINRA as an organization does and what we do. FINRA is an acronym for Financial Industry Regulatory Authority. Oftentimes, we're called as Wall Street's watchdogs. What we do, our mission, our goal, is to maintain the integrity of the market and protect investors such as yourself who are buying and selling products in the stock market, in the equities, fixed income, or options market in the US. So we monitor around 12 different exchanges, and we regulate more than 3,800 firms and around 634,000 brokers. We do this by ingesting around 37 billion transactions every day. In terms of big data, so that can go up to like 100 billion transactions on a particular day, and recently it even gone up to 135 billion, I think. And we store a lot of data in the cloud. We completely operate in the cloud, and we store like more than 25 petabytes of storage in the cloud. And when we take all this data and reconstruct the market, it can come up to like trillions of nodes and edges, showing the complexity of the data that we collect. Once we collect all this data, part of our department, they run hundreds of surveillance programs on top of this data. These programs are more like algorithms that are looking for like manipulative activity or compliance breaches in the market data that we collect. So a typical example for these surveillance programs can be our programs called Best Execution and Order Protection that mines the billions of trades and orders that are coming in every day. And they're looking out for you as an investor. When you place an order through your broker or other channels, did you get the best price that was available for you in the market at that exact point in time? So that's one of our programs. So we have hundreds of programs like that. So the session takeaways. So what we hope by the end of the session, what you get to take away is you get an understanding of how FINRA uses the cloud infrastructure, different scaling strategies that we apply on our cloud resources, and some of the data visualization principles, the challenges and strategies with big data visualization, and how the visualization principles they apply in the context of market surveillance. So let's start with a very high-level FINRA cloud architecture. So we ingest a lot of data, as I mentioned. So that's on the rectangles at the rightmost or leftmost to you. So that's all the ingestion coming in. The exchanges are a main contributor for us, for data-wise. Once the data has come in, the very first layer is the intake layer. That's where all our ETL processes run. They take care of ingestion, validation, normalization, and linkages. And once that is done, it pushes the data to the storage in the management layer. Storage, we operate in the cloud. As I mentioned, we use mainly Amazon's S3, which is a scalable storage solution, and Glacier, depending on the archival strategy. We manage the data in the cloud using our cloud-managed data management product called as HERD, and UDC, which is the front end for HERD. HERD is a homegrown FINRA-built product for managing data in the cloud. We built that when we actually migrated to the cloud, and it has since been open sourced as well. The final layer is the analytics layer. The analytics layer has numerous applications that are targeting for, that are ingesting data from the storage layer and are addressing different business needs. And these applications are most of them are built with latest open source technologies to ingest the data and present and solve a business problem for the users. So I mentioned about the third layer, the analytics layer. So if you zoom into that analytics layer and you focus on the applications that are mainly dealing with market data, this is the picture that you would get. So what you're looking at is a list of internal FINRA applications that are mainly, portfolio that are mainly dealing with big data set. Each of these applications are driven for different business needs. For example, Diver, one of our applications, is basically focused on providing self-service capabilities to our business users to build personal data marts around billions of rows. MERS is more like a BI type of platform for building aggregations and reports on the market data. One of the new tools, a product that we built out, is called SURF, which is Surveillance Review, and which stands for Surveillance Review and Feedback. Most of the principles, the visualization principles and architecture principles that we talk about in this particular session is built around what we did that were used for building SURF. So what is the purpose of SURF? SURF, as I mentioned, stands for Surveillance Review and Feedback. I mentioned a few slides back that we run hundreds of surveillance programs looking for like manipulative behavior or abusive activity in the market. All these programs kick out lots of violations, and we call them exceptions in our world. And these can be in millions. So our business users, our surveillance analysts, are tasked with looking at these violations and recommending a correct approach to resolve them. Maybe it goes to the lawyer, or it gets closed saying that it's an invalid violation. So SURF as a tool provides our business users these three functionalities. An interactive data access, they have like drill down capabilities on hierarchical data set. It provides appropriate visualizations on top of the data so that they can do their analysis much faster and more efficient way. And lastly, it works as a machine learning feedback tool. Some of our programs are driven by machine learning models. So these models, some of the models are practicing supervised machine learning techniques, and they need feedback to keep the model healthy over a period of time. So that's where, with this tool, we give that power to the users to provide feedback directly so that the model can get better over a period of time. So this is the underlying architecture for SURF. So as I mentioned, this is completely on the cloud. We have the load balancer, which is channeling the traffic to the applications. We have application distributed across multiple availability zones. The ones that you see, A and B, those are different availability zones. We actually have more than 2 availability zones. And there are 3 layers to it. The very first layer is the container layer. The container layer is managed by ECS, which stands for Elastic Compute Service, Container Service. And the ECS is tasked with managing the tasks or the containers that are deployed in these underlying host machines. They manage the life cycle of those containers. That's where the core application logic is deployed. Then the second layer is the Presto EMR layer. As I mentioned, we have vast amount of data violations getting kicked out and getting stored in S3. So Presto is the way for us to get to the data that's in S3. So when the surveillance programs kicks out these violations, sometimes we take that, make performance copies, different compression techniques to make that performant for users. And we use Presto that's installed on EMR, Elastic MapReduce, which is a framework for managing these big data frameworks like Hadoop. So Presto, as you know, is an open source distributed SQL query engine. It's mainly built for querying big data sets in an interactive fashion. The third layer is our RDS layer. RDS is a managed service, again, for managing relational databases. So we use Postgres for our transactional entries. And that RDS takes care of replicating it across availability zones and doing all the mundane things that goes with managing the database. So if you look at this architecture, pretty much every component in this architecture is elastic and scalable in nature. We also have the CloudWatch monitoring connected to the application, collecting metrics from the application, and depending on whether the threshold is crossed or not, it would trigger the scaling mechanism. So we have scaling enabled at the container level, the ECS auto scaling, what we call it reactive scaling, and we're working on enabling scaling or at the Presto layer, we call that predictive scaling using machine learning techniques. We'll talk more about that in the next few slides. So reactive scaling. A typical way to deal with varying load is to over-provision. The problem with that is it is very static in nature, and we're only adding cushions to it. Modern cloud infrastructure providers like Amazon gives you a complete toolkit to manage, to effectively schedule event-driven scaling techniques. ECS auto-scaling is one such toolkit. ECS takes care of, Elastic Container Service, ECS takes care of scaling up and down the nodes depending on the varying load. And how you actually trigger the scaling mechanism can be configured using a CloudWatch that's connected to the system. ECS is similar to Kubernetes or Mesos that's available in the open source world. In addition to the reactive scaling, we're also building, we're getting ready to roll out a predictive scaling technique using machine learning. So why exactly do we need predictive scaling if we already have reactive scaling that's by default provided by the cloud providers, which is just out of the box. You can just go to the AWS console. You can put in within a few clicks, you can enable the reactive scaling techniques. So one reason is for the container layer, bringing up a container into life is pretty fast. It works without any impact. But if you're trying to add an instance to a cluster of machines, in our case, the Presto EMR cluster, there is a long warm-up time associated with that, and the very request that you're trying to address by scale-up, you won't be able to meet it because it's too late by the time the instance becomes fully functional. Now, in addition to that, there is a slow conversion to required capacity, meaning if the load on the server scales up pretty fast in a short period of time, the reactive scaling may not scale up fast enough to meet that demand. And lastly, since we have our application and we can see the usage pattern of the users and it also depends on a lot of application-specific features like how many violations got ingested into S3 and how many are pending review from analyst users. All that can be built into machine learning features, and they can be used again for predicting the scaling techniques. So what we built is a machine learning model that can predict the potential load on the server before the time of the need. The model was trained based on usage statistics from the users from the historical usage data, and we also built custom application features. Like I said, for example, the data we surface in our application are ingested from S3 by external applications. So we built ML features around those statistics. What are the ingestion statistics, and how many violations are pending, and then we feed that into the model. Once the model is trained and deployed to production, it can start making predictions based on the statistics that are available to it at that exact point in time. And once a prediction is made, our serverless Lambda wakes up and then sends a scaling action to our instances so that instance can be up and running before the time of the need. So with this, the engineering side of the task is complete. As I mentioned, we're going to approach that on the engineering side and the data visualization side. So now I'll hand over the presentation to Daniel, who will talk more about the visualization principles and different blueprints that we use. Thank you.
Good morning, everyone. Let's talk a little bit about data visualization, right? Let's make just a small pause. Say something. In any clear night, if you look at the sky, more specifically to the northern sky, in the direction of the Ursa Major constellation, you should be able to see it. 15,000 galaxies distributed across the sky. We're talking about an immeasurable number of stars, constellations, black holes, comets, and whatever suits your imagination. And what does it have to do with data visualization? It has everything to do with data visualization. This is a picture, it's a mosaic, actually, of a series of pictures taken by the Hubble telescope and a lot of different ground equipments over several years. This was published a while back by the folks at NASA. And this is the representation of the 15,000 galaxies that I mentioned. We could have a list of IDs for these objects, of coordinates in relation to each other and in relation to our own planet. But by looking at this picture and by happening to know the story behind it, by happening to know that this represents almost everything that we can see at this point in the universe, I think it's a stronger display of a concept of something that we're talking about. And this is what I want to talk about. This is one of the things that I want to talk in terms of data visualization. The idea is to allow you to look into a lot of data, and sometimes, as in this case of the 15,000 galaxies, something that I cannot even start thinking about, the dimensions involved, the numbers involved in this data set, but having a visual representation of it allows me, to discuss and invites me to think about what this thing represents, right? What are the underlying universe around this picture? And moving forward, data visualization is not something new, actually. I have here a couple of maps. The first one is attributed to a Greek, Anaximander. It was his vision of the known world a few centuries ago. Unfortunately, this is just a reproduction based on description because the original one was lost. But it was a vision of the known world, right? So everything that they thought was the world, everything they knew was in this small picture, everything they knew. Then we have the Mercator map that is to this day the most known projection of a map that is used for representing our world. And of course, we cannot leave this out. We have Google Maps that is, I would say, one of the greatest examples of data visualization, both in terms of the way a huge amount of data is displayed in a very effective and useful manner. So we can only hope to achieve this kind of perfection in our own visualizations on a daily basis. Now, when we talk about data science and what is the actual focus of this conference, we have in data visualization something close and something very similar in terms of a process, right? So usually we start with an interesting problem or with a question that we need to answer, or even a goal. We want to prove something, we want to demonstrate something, right? So we already think we know something and we want to share that with the world, so we want to prove that. So in order to do that, we collect a lot of data, we explore the data, we prepare the data for representation, talking specifically about machine learning and all that cool stuff. We develop different models and we apply different algorithms on the data in order to prove our theory or to look for something that we didn't even know about it before starting this process. And after we do all of this, using that cool Amazon infrastructure, all different kinds of boxes, ECS containers and so on and whatnot, we come to a point in which we need to communicate our results, right? Or we need to look at the results of different models and make decisions and decide, okay, what we're going to do about this. And specifically in the field of market surveillance, we need to decide, okay, this is something interesting. Is this something suspicious? Is this something that we need to go after? So we need to move on to that. And in order to take all this data and put in a cool, nice representation, what we do is called visual encoding, right? So if we look at this small data set that I have here, it's just a few variables. There are just 3 variables with different types. I have some numbers, I have some classifications such as whole, high, medium. And what we do in data visualization is basically encode this data in a visual representation. So we take raw values and we turn into something that can be visually grasped, visually interpreted. And we have a lot of techniques for doing that, but we have some basic visual elements that we can use. So for example, we can take a value and we can position this value in a specific grid or axis in order to convey that particular value it's bigger than another one. Other options that we have is to represent values based on shapes. So we have shape 1, 2, 3. We have a circle, a triangle, and a diamond for values 1 to 3, and so on and so forth. Other things that we can use is color, for example, for saying that one thing it's different than the other, or for example, if we use color scales, we can say that something is hotter than other, right? So although you cannot sense color temperature, you can say, okay, red is a hotter color than blue, for example. And this is all that we actually do in data visualization, right? So we take raw values, we decide on the way that we're gonna encode those values into visual elements, and we draw this somewhere, right? So it should be easy enough. It should be pretty straightforward. Yeah, but unfortunately, it's not how it goes most of the times. So here we have an example for the techniques that I showed before. So, for example, we can encode events over time, and we can represent their distribution over time based on how we plot them on a time axis, for example. Or, for example, we can say that there is an event here that represents a larger amount of money based on the size of that particular visual element that we chose to represent that event. And other things, so one aspect that is very frequent in our field is the need to group things. So we need, for example, to group firms based on their profiles or on their usual behavior in terms of trading behavior and all of that. So we need basic ways of grouping things, and we can do that by, say, for example, using colors. Everything that is the same color, you can use. You can say there's part of the same group. Other things, for example, we use size, for example, for representing volume, but you can also use position. As in the last example, I'm just positioning a particular event in a volume axis to say, okay, this is a larger event than the other ones. Now, there's some principles for visual encoding, and those are just a few examples. And there are principles regarding data visualization. And the first one is that we need to stay true to the data. Data visualization, it's not actually only about displaying pixels or displaying more information. As the name implies, and as we can see, data comes first. So the most important aspect of data visualization is the data. And they're so important then, that the next rule is also stay true to the data, right? So if you're trying to show something, if you're telling a story with your data visualization, we're going to talk about stories later, this is the most important aspect of it. Whatever you show needs to be proven by data. And moving forward to some other principles regarding data visualization, and some of them are very much related to data science principles. For example, we also start with interesting questions, theories, or things that we want to demonstrate. Often we already have something that we wanna show. We already have a theory that we wanna share with everybody, and say, okay, we need a cool way of demonstrating that with visuals. So we can start with that. And there are basically two types of visualizations that we apply, and it's basically the two types of visualizations that we apply in market surveillance. One is exploratory, in which we look for different things. We look at the data trying to find something. Sometimes we know what we are looking for, sometimes we don't know. We just want to look at the data and see what is that all about, right? And I'm not sure if I need to say this in the context of surveillance, is that what we are looking for is not necessarily clear, right? And J-Paul was mentioning market manipulation, market manipulation behavior and market manipulation activity. Usually, whoever is trying to do that doesn't want you to see what is happening. So we need to look into the data and look for that. The other thing, the other way of looking at the data is explanatory. So, for example, in our context, For example, we were able to find something. We were able to find some suspicious activity. And at some point, we need to say, this event, maybe this trade or the sequence of events or these things that were happening in a time frame, these were illegal activities, or these were not, these events were breaking the rules. And we need to be able to show the rules in a visual format, usually, and demonstrate visually how that particular scenario it's a violation. So it's a way of explaining what happened with visual elements. And other things that are important in terms of data visualization principles is that we can look at the data in order to ask the data how does it make, how would it make sense to show this data as? So for example, if we look at a time series data, right, or we look at time-sensitive data, it makes sense to show time visually, to show events happening over time. If you're looking to see, if you're looking, for example, one particular scenario that we have in surveillance, market participants or people or participants working together to break market rules, what we want to look for in this case is not only events over time, but we want to be able to establish relationships between the different participants that we're trying to look at, to investigate. So you can look at the data and have an idea of and also having an idea of what you're looking for, how you could represent that data. Another point that is very important, as I said, data is the most important thing, right? So you don't want to get the visualization in the way of the data, in the way of what you're trying to show or what you're trying to convey. You want the data to speak by itself. So you want to keep simple. You want to show the meaning of the data, and you also want to have all the appropriate context for the data, and nothing else. So, for example, I have an example of a 3D pie here. We don't want to add cool, fancy effects to a data visualization just for the sake of the effect. It needs to have purpose. It needs to have meaning. It needs to have something associated with that. If your objective was to show a cool thing, maybe showing a cool thing in a 3D model would be just enough. But we should stick to the objective, to the goals. A little bit more about our own context of market surveillance and data visualization. Usually, what we do is, not usually, but in two different moments, we look across the whole data set that we have. We look across the whole market, where we can see hotspots and interesting events. And based on that, we can zoom in, as I'm showing here, and at this point we can reveal more interesting data, and we can bring different contexts into a different visualization that is no longer across the whole market, but on the specific events, on the specific time frames, and on the specific things. But we have some challenges with that, because we're dealing with 100 billion records all the time. So we have problems with the volume by itself. We have problems with, we have challenges with dimensions. So whenever we look at a data set, we're talking about 100 different dimensions, 100 different columns that sometimes we need to look into. Also, we have a very fast pace of experimentation, investigation, and of proposing new and different models for surveillance. So we need to be able to prototype and come up with different visualizations rather quickly. And there are limits as well on what we can display at a given time, right? So we have, in this case, we have quite a big monitor here, but usually we have to deal with the limits of, the hardware that we have of our own perceptions. We can look at 15,000 galaxies, but you cannot, look at all the galaxies and understand what is underneath that at a given time. So we need to establish context for that. And this is just, again, the numbers that we are dealing with and that we have to deal with every time we think about creating a visualization or come up with a different prototype or a different ML model, and we need visualization support. But it's not all despair and crazy despair of not being able to do this. There are some techniques, some things that we can do, and some things that we actually do in order to to deal with this huge amount of data. One of the basic things that we have to do is bring big data to not so big data. So at this point, we need to aggregate our data. We need to filter. So for example, in some cases, for a specific context, we already have a context and a way of filtering the data. So we take this context, we dive into it, and we can narrow down what we want to see. Another way is aggregating the data, as I said, or sampling the data. That is it's a little bit more, it's a smarter way of filtering the data, right? So for example, we have statistic algorithms for doing that, and we also have some ad hoc procedures for sampling the data. You can define your own algorithm for sampling the data, and that way you look at potential candidates for whatever you're looking for. And another thing that is the one that I like the most is looking for scalable blueprints for visualizations. And what do I mean by that? I'm talking about different types of proven visualizations that we can use for representing known types of data. I'm just going to jump from the presentation here to our application catalog. I'm just going to show very quickly 3 examples that we have for scalable visualizations in time series, multidimensional data, and relationships. So this is part of our application. I'm running, a small subset of what we have. I'm running locally, but just to give you an idea. Oh, I need to finish the presentation so you can actually see that. Sorry about that. Okay, here we have it. So this is not a FINRA-specific thing. There are common visualization galleries all around, but here we are trying to capture what is useful for us. So, for example, the first one. When we look at time series data, this is a very simple example. Usually we need a lot of space for representing that data over time, and we need to do this all the time when looking at market data. So all we have is trades, trade events, and all of that happens over time. So one way that we found that is very useful for us to represent this type of data is to apply the horizon graph concept, in which we split what you're seeing here across the whole y-axis. We split the whole y-axis in different bands, and then we overlay the data on top of, we overlay the bands on top of each other, and that way we can collapse and compress this visualization into something that is going to be as small as this one. So you still have the same data here, but since we split the series in different bands and we overlay them on top of each other, we can have a single time series in a very small size, occupy a very small space, and we can replicate that for other time series that we want to compare. There are some good examples out there for this case, and it's something that is particularly useful for us as well. The other one is for dimensions, and I'm not sure if you know about. This is a parallel coordinates chart. When we are doing with ML models, when we are dealing with dealing with multidimensional data, sometimes we need to look across all the dimensions at once and be able, to deal with those dimensions at once. In this case, I have just a handful, but in this case, we should be able, for example, to filter the data based on a range of one of the dimensions that we're interested in. And we can do that for different features at once to see how many, for example, how many observations we have that will fall into that specific grouping of features. This is another one. And another one, this is more experimental, something that we are trying now. It's with hive plots. Hive plots are kind of similar to parallel coordinates, but you have much more flexibility in terms of how you organize the axis, how you organize the angles, and you distribute the relationships in a way that would make sense, that is related to the data that you're trying to show. For example, in our case, organizing firms and symbols over an axis based on how much that symbol is traded or how much activity we see in that particular symbol. So these are the kinds of visualizations that we're experimenting with because they kind of address some of the challenges that we have. So this is pretty much what I wanted to talk about. Let me just finish with a different one. That is our idea for market surveillance data. So it's something like this. We have all the market data that we need in order to surveil it and to analyze it. We score this data and we generate what we call score observation. Let's say, for example, this trade, it has a suspicious index of between 1 and 10. It's not actually like this, but bear with me. Then we have different algorithms generating surveillance output, and on top of that, we still have contextual data that we need in order to understand what is happening there. And what we're trying to do is to take all these layers and in a similar way that we have in map layers, in geographic maps, we want to be able to overlay that, put everything on top of the same scale, the same structure, and look across our data using all those specific layers or removing and adding different context and surveillance data layers as needed. So this is what we are moving forward. At some point, we're going to have something like Google Maps for market surveillance. So we'll see. Well, and yeah, now that's pretty much what I wanted to share with you. Do we have any questions? This is a way of looking at it. This is more of a conceptual idea in the sense that we can overlay the data on top of each other. And usually, for example, if we take a scored observation that is produced by one surveillance model, for example, and we take another and another and another, and we overlay them, we can see, for example, the concentration of activity across models. So you can say, okay, this is just a way, for example, of showing that different models agree with the fact that there's something happening here. So, and this is something that, yeah, not necessarily based on color, but based on the data, right? The color here we use as an example, but ideally you should have a transparency level from one level to the other. So you see that it gets darker and darker the more you have activity concentrated in that specific point. And this is something that we hope to be able to apply on different types of visualization, not only on this one.
So whenever you start doing these more complex
We actually work with business folks in order for ourselves to understand what is the underlying data that we're using. So we don't do this by ourselves, right? We need to work with people that actually know and understand, for example, one specific surveillance scenario, one specific illegal activity, and we need to discuss with them and understand what is important about this scenario, what is important to see in this context, and based on that, we come up with different kinds of visualizations. Not sure if I answered the question. Yeah.
I guess I'm looking for more practical techniques to make it more like, easy to understand, I guess.
Yeah. Well.
If I showed that at work, they would probably be like, I have no idea what this is.
Yeah. In this case, you actually need to apply that in a context that makes sense for. That makes sense for your business area or for your own scenario, right? There are some principles they're independent of whatever you're trying to show, right? Colors, positions, all of that. Those are common principles across everything. But when we talk about market surveillance, for example, volume concentration is something that is specific to market surveillance. The same way as, for example, I don't know, electricity resistance to muscle could be something specific to medical field. I'm not sure if it is, but it's something like that. So you still need to have the context. And again, that's why data comes first, right? Because the data is going to drive this, not the cool 3D axis moving technique. When you have raw data, and since we're talking about spreadsheets and stuff like that, you can actually use that up to a certain point. But for example, if you take 100 rows of data of a summary report or something like that, you only be able to look at that and start inferring things from what you're seeing up to a certain point. After you reach a threshold of data volume, and that's not a big threshold, it's useful to aggregate that and to summarize that in visual representation. And this is basically what we're doing. For example, if we take a whole line, right, with information, and you turn that into 4 or 5 pixels of information, and that is still relevant, if that is still relevant, then you can condensate a large amount of data into a small resolution. But if you need to look into the details, of course, you're going to have to go and look for the raw data to see what's there. So visual representations are not going to replace your data. That is something that's important as well.
And actually, we're going to hang out here, so if you have more questions, it looks like we're getting kicked out.
Yeah, oh.
So we can hang out there.
Sorry, okay. Thank you all for...
Thank you.